And much like, I think it was lesson 7.2, 7.1 dealt with exponential functions and their graphs, and then 7.2 we looked at transforming them. This is the same kind of idea. In 8.1, what we look at is what the graph of logarithmic functions looks like. We did that yesterday. Wasn't a big deal, but today we're going to make it a big deal by talking about the transformations. So basically what we're going to be doing is transforming functions that are logarithmic. We're also going to be doing a second thing. So this is a lesson that's got three little mini things within it. We're going to be looking at transformations of logarithmic functions. We're going to be doing more application problems, but these ones will be logarithmic in nature. And then we're going to be looking at something called the change of base formula, which will allow you on your calculator to calculate any logarithmic value, even though it's not base 10. To begin with, we have an example where we have log base 3 of x plus 9, quantity x plus 9, and then plus 2. We want to sketch that. We want to sketch it without the use of a calculator. So the thing that you need to appreciate here, I think, is that we're going to look at log base 3 of x in order to decide what log base 3 of x plus 9 plus 2 looks like. And you know, even before we start to talk about what y equals log base 3 of x looks like, which we learned yesterday, but we'll review it, you should understand that the changes that are happening here is we are going to be shifting log base 3 of x 9 units left and 2 units up. You should be able to look at this function that I'm highlighting and see that you've got an h value of -9 and a k value of +2. So if we can just figure out what log base 3 of x looks like, we can shift it. Well, here's where things get a little bit, I guess involved is the word. I know what log base 3 of x looks like. I'm guessing that most of you don't. So we have to go back to yesterday and remember that log base 3 of x is the inverse of y equals 3 to the x. So what I'm going to be doing here is using my knowledge of inverse functions to determine what this function that I'm now highlighting, I need to know what this function looks like so that I can shift it 9 units to the left and 2 units up. But in order for me as a student to figure out what that looks like, I have to remember that these are inverses. So it turns out what I'm going to put on my grid will be 3 graphs. The first graph is going to be y equals 3 to the x. I'll use blue for that. So I'm going to graph y equals 3 to the x in blue. And we learned back in chapter 1 that 3 to the x is an exponential function with an asymptote that will be the x-axis. It has a y-intercept of 1. And every 1 I go to the right for y equals 3 to the x, y gets tripled. So when x is 1, y becomes 3. When x is 2, y would be tripled again, which would be 9, but I can't fit 9 on there. If I go 1 in the opposite direction, y gets divided by 3. So these 3 dots represent what y equals 3 to the x looks like. And that's good enough for what we're talking about here. Now what I'm going to do is graph in red y equals log base 3 of x. So I'm using the idea that everything gets switched. The asymptote, which was a horizontal asymptote at y equals 0, now becomes a vertical asymptote at x equals 0. The y-intercept of the blue graph is 1, which means the x-intercept of the red graph is 1. If you get really good at this, you can kind of reason out what the pattern is here, because with the blue graph, and this is hard to follow, you need to listen carefully to the words. With the blue graph, every time you go 1 to the right, you triple vertically. Well, that means that on the red graph, every time you go 1 up, you triple horizontally. And this point that I'm just drawing right now can also be arrived at. I'm going to erase this in a second, but it can also be arrived at by taking 1, 3 and swapping it so it becomes 3, 1. We can get that third point on there by doing the same kind of thing, swapping the x and y coordinates. And I erased that other point. It should be here. If you wanted to, and I wouldn't do this, I'm going to do it and then erase it. You know, you could point out to yourself that this is in fact a reflection in the line y equals x. But I'm not too concerned about that. In fact, all I'm really concerned about, everybody, is the red graph. This is y equals log base 3 of x. Just so you can follow along, I don't care if you have different colors or not, I am going to use green for the final function, which is what we are asked to sketch the graph of. So blue was y equals 3 to the x. You didn't really need to graph that as long as you know how to graph log base 3 of x, which is in red. Now I have to take this graph in red and I have to shift it 9 units to the left and 2 units up. So before I do that, does anybody have any questions so far about those first two graphs? All right, so if we shift this graph 9 units to the left, that means the asymptote, which is at x equals 0 on the red graph, will be at x equals -9. And you know, we don't really need to start counting squares here. If I take a look at this point, it is a third to the right of the asymptote. So when I shift it, it's going to be a third to the right. This point is 1 to the right of the asymptote. So if I shift it, it's going to be 1 to the right. This point is 3 to the right and 1 up from the previous point. So if I go 1 up from the previous point and 3 to the right, in total, I get that. So the graph that I'm drawing now, whoops. The graph that I am drawing now is the graph of y equals log base 3 of x plus 9 n bracket plus 2. Does anybody have any questions with 1a? All right, 1b, we're asked some information about this graph. What's the equation of the asymptote? Well, you can see that the asymptote is at x equals -9. You can probably make a note that the asymptote will always be at x equals h. It has to be, because the asymptote of log base b of x is at x equals 0. So when you shift it, it's going to be at h. The range is still any real number, but x is greater than -9, which in this case is x is greater than h. Is it possible that you could have a logarithmic function where x is less than h? Yes, if there's a horizontal reflection first. So if you reflect a logarithmic function horizontally with a negative b value, it will flip over and x will be less than wherever that asymptote is. So that's the domain and range. The y-intercept, if it exists, so let me write the equation of the function. The function is y equals log base 3 of x plus 9 plus 2. A y-intercept is where x equals 0, and x-intercept is where y equals 0. These are the rules we use. So I'm going to rewrite the equation for the y-intercept, but just put in 0 for x. And I end up with y equals log base 3 of 9, then plus 2. This should be, if you're not quite there yet, all I'm saying is you need to get there soon. Like by the time we come back from Christmas holidays, I hope everybody will have not forgotten that this is 2, because log base 3 of 9 is the exponent to which you raise 3 to get 9. This thing we were doing yesterday where you would say, well, let me think about this. Log base 3 of 9 is some number, 3 to that number. You shouldn't have to do that in this case. You should know log base 3 of 9 is 2. And then we have plus 1, which means the y-intercept is at 0, 3. And I don't know if we extended that graph that we drew. I didn't draw it really well, but if you extend it, it's going to end up crossing at, just a second here. Did I write something down wrong? Yeah, this should be a 2, eh? Thank you, Colton. The y-intercept then is at 0, 4. Are we okay with the y-intercept there? Okay, the x-intercept we let y equal to 0. So we have log base 3 of x plus 9 equals 2. I'm going to subtract 2 from both sides. And now, how do you go about finding x? Well, this is what I was talking about yesterday. If you hit a brick wall with logarithms, rewrite it in exponential form. So if I rewrite this in exponential form, negative 2 is the exponent to which I raise 3 to get x plus 9. Which means x will be equal to 1 over 3 squared, that's what 3 to the negative 2 is, minus 9. Can you work that out for me, please, in decimal form? And somebody type what it's equal to in decimal form. That's 1 over 3 squared, not 1 over 32. I think it's negative 80 over 9, which is negative 8.8 repeating. If we go back and we look at the graph that we constructed, why is it not crossing at negative 8.8 repeating?
You forgot to translate it 2 units up, I think.
Oh, jeez. Same thing I did the other day. I'm sorry about that, you guys. And that's why I was kind of pausing, because it didn't even look like it would have a y-intercept of what it should have been. So that green graph, man, oh man, I guess I just need a break. That green graph needs to move up 2 units. So this point goes up 2, this point goes up 2, this point goes up 2. So when I shifted it over 9, I should have just kept going over 9 and up 2. And you can see now that it's crossing way, way, way close to negative 9, which will be the negative 8.8 repeating. Thank you for catching that, gentlemen. So we end up with, for a x-intercept, negative 8.8 repeating. And if you want to put that into fraction form, can somebody confirm that it works out to negative 80 over 9? Okay, good. So the x-intercept is negative 89ths, 0. All right, let's try one more. Let's translate y equals log base 2 of x, and I'll see if I can not screw it up this time, into y equals negative log base 2 of 2x plus 6, but we have to remember to factor that 2 out before we jump to any conclusions about horizontal translations. Would everybody agree, first of all, can I get some people to agree, yes or no, that we have a vertical reflection going on here? Definitely, right? We have a horizontal stretch. Can I get some of you to type into the message window or the chat window, whatever you want to call it, the factor that the horizontal stretch is by? It's 1/2, which is the reciprocal of b, good. And then we have a horizontal shift. Is it 3 units left or is it 3 units right? Definitely left. So we start off with log base 2 of x, and I am not going to draw, like I did in the previous question, this to figure out what log base 2 of x looks like. You certainly can, but I'm going to kind of push you a little bit here because you should know that the original function, I will go with red. This is y equals log base 2 of x. You should know that the original function for a logarithmic function has an asymptote here. And since exponential functions that are simple have a y-intercept of 1, this has an x-intercept of 1. Since for exponential, when x goes up by 1, y would double, here, when y goes up by 1, x doubles. And when a y goes up by another one, x doubles again. And y goes up by another one, and x doubles again. If we go back 1 on an exponential, things get cut in half. So if I go down 1, things will get cut in half horizontally. You should be able to come up with this graph kind of on your own. In fact, you should recognize these now. This is what log base b of x looks like. And just to let you know, you see this point right here? Whatever the x coordinate of that point is, that will be the base of the logarithmic function. So that's what log base 2 of x looks like. What do we have to do here? We have to reflect that. Then we have to stretch it horizontally by a factor of 1/2 and shift it 3 to the left. I think the first thing that you should understand is even though we are going to be messing with the vertical and horizontal features of the graph, none of those would change the asymptote's location. The only thing that's going to change that asymptote's location is an h value, so we know that the asymptote will be at -3. I'm going to reflect these first, and I will use blue as an intermediate kind of point that we will track. When I take this point and I reflect it vertically, it doesn't move, but then I stretch it horizontally by a factor of 1/2 and it goes there. If I take this point and reflect it vertically, it goes here, and then I stretch it horizontally by 1/2 and it's going to be here. This point, reflect it vertically, stretch it horizontally by 1/2, it's going to be here. We don't need to do every single point. I'm going to do one more. I'm going to choose this point now. I reflect it vertically. Stretch it horizontally by 1/2, and it's there. So each of those points has been reflected vertically and stretched horizontally by 1/2. Now I simply need to move them all 3 to the right. And I'm pretty sure here, but I haven't missed anything, right? There's not one other transformation that I'm not looking at. That's it. Reflection, stretch, translation. So I'm going to shift all of these to their relative positions next to that green asymptote. In other words, this blue point right here is very, very close to the asymptote, so it's going to be very, very close to the asymptote here. This point that I'm covering up is half away, so it's going to be half away. I think you get the idea. We're just going to shift all of those points over now. And we get the following graph. And that's it for part A of this question. Any questions with part A? Okay, domain, range. I don't know if I asked about the equation of the asymptote before. I did. The equation of the asymptote here would be at x equals -3 because h is -3. The domain is x is greater than -3 because the graph is to the right of that asymptote. The range, the graph goes up and down forever, so y is any real number. Any questions with domain and range in the equation of the asymptote? All right. X-intercept and y-intercept, what are we looking at here? Y equals negative log base 2 of 2x plus 6. Can I get a yes in the chat window if that's correct? Good. Thank you. So y-intercept is when x equals 0. This is y equals -1 times the log base 2 of 2 times 0 plus 6, which is the y-intercept is -1 multiplied by log base 2 of 6. And we're not going to calculate that yet. What I will tell you is whatever number that is, if we go back and we look at this y-intercept here, it's going to have a value of -1 times log base 2 of 6. The reason why we're not going to calculate it right now is you don't know how to. All right, what about the x-intercept? The x-intercept is found by letting y equal to 0. So I'm going to multiply both sides of this equation by -1 to get rid of that negative in front of the log. Then, because I'm looking at this going, I don't know where to go, I remember that you translate it to the other language. It now becomes 2 raised to the 0 is equal to 2x plus 6. So 0 is the exponent to which 2 is raised to get the argument. That's 1. So 1 equals 2x plus 6. That's pretty easy to solve. 2x equals -5. So x equals -5 halves, or -2.5. And if you go back and take a look at your graph, or I go back and take a look at the graph, you can see that's exactly where it crosses on the x-axis. Any questions with example 2? All right, example 3 is the opposite of this. It is saying that the blue graph, well, my blue graph, is y equals log base 4 of x, and it's asking for the equation of the red graph. Well, you can see the asymptote is the same. The only thing that's changed is this blue point. Well, the whole graph has changed, but this key point is now here. That blue key point was 4 away from the vertical asymptote, and now it's 1 away, which means we're talking here about a horizontal stretch by a factor of 1/4. Color means nothing here in terms of what I'm just writing. I'm just saying that to go from blue to red, you stretch horizontally by a factor of 4. We should know that that means b is equal to 4, which means that this equation of the red graph will be y equals log base 4 of 4x. Questions with 3a? Pretty simple idea, but I put this question in here because later on today, if I remember, I want to come back to it and show you that there's a deeper meaning behind what's going on here with this question. Take a look at b. I think it's pretty obvious that log base 4 of x has been reflected vertically, which means that a is a negative number. I think it's also pretty obvious that when you reflect this blue point vertically, it ends up here, which is only 1 away, and yet this red point is 3 away. So not only are we reflecting vertically, but we are also stretching by a vertical factor of 3. Well, that means that the new equation is y equals 3 log base 4 of x. Any questions with example 3 at all? All right, so now we got to talk about something. There's this formula. I don't know why it got cut off. There's this formula that's on your formula sheet. And what it is it's called the change of base formula. And what it allows you to do is change any logarithm with any base to a new logarithm calculation with whatever base you want. So I want to demonstrate this to you using numbers. Let's say that I wanted to figure out what log base 2 of 64 is on my calculator. Now, you can do this right now, but you're not going to use logarithms. I want everybody to figure out what the exponent is that 2 would be raised to get 64. To what do I raise to get 64? It's 6, right? 2 to the 6. We can work that out. 2 times 2. We can just work it out. It's 6. So we do have a log base 10 button on our calculator. And what this change of base formula is saying is if we want to change it from log base 2 to log base 10, we're going to be dividing by 2. We're going to be dividing 2 logarithms. And the logarithm on the top will be the logarithm of the original argument. In other words, it would be log of 64. And the logarithm on the bottom is the base A logarithm, the new base logarithm of the old base. Now, I want to show something to you here. I'm kind of interested in this kind of thing. It intrigues me. If I figure out log of 64, it turns out log of 64 is an irrational number that goes on and on and on forever. It really is an irrational number. And log base 10 of 2, remember that log key is base 10, is also irrational. But if I figure out what log of 64 and I close the brackets on the argument divided by log of 2 is, I get 6. We do not need to worry in high school math as to where this formula comes from, but it's a formula that we can use for calculations. Now, I told you in part 3 of example 2, we will figure out what this is in a minute or two. Well, it's going to be negative 1 multiplied by log base 10 of 6 over log base 10 of 2. I'm just using the change of base formula because that's the log base 10 button is what I have on my calculator. So if I take log of 6 divided by log of 2, and then multiply by negative, it's negative 2.58 is the y-intercept. And that arrow, whoops, that arrow that I drew, which I'll just highlight for you, was indicating where the y-intercept is, and it is in fact at negative 2.5, whatever we got. So that's the change of base formula. So let's take a look at 4a. I guess we're not going to need the change of base formula for 4a. If I were to rewrite this function in 4a, I could write y equals 2 log base b of 3 times x plus 4. Remember that the asymptote tells us where the domain starts from. So the asymptote will be at x equals negative 4. And this is a little confusing here, but your domain is still going to be x is greater than negative 4. Don't let this fool you. This is the base of the logarithm. There has been no reflection here in terms of horizontal stretches and reflections. So if you were to sketch this graph, you would get a domain of x is less than or greater than negative 4. Has nothing to do with the change of base formula. Any questions with 4a? Okay, I guess 4b is where the change of base formula comes in. Evaluate these and rank them. So we're going to rank them from smallest to biggest. If I want to know what log base 6 of 24 is, I can go log of 24 divided by log of 6. It's 1.77. Log of 66 divided by log of 3 gives 3.8 roughly. So far what we're dealing with is that this one is bigger than the first one. The next one is log base 10 of 3. Oh man, we don't need to use the change of base formula. Just go log of 3 because it is base 10. But if you wanted to, you could take log of 3 divided by log of 10. Anyway, you get 0.48. So 0.48, that's even smaller than the first one. And then log base 20 of 5 would be found by taking log of 20 divided by log of 5. Logarithms, just like exponents, are deceptive. You get 1.86, which is smaller than log base 3. I got that backwards. It's log of 5 divided by log of 20. I was wondering why it was so big. Is a little bit bigger than log base 10 of 3. My plan for representing these by sizes of dots wasn't really maybe the best well thought out thing. You would discover that this is the smallest, then this one is bigger, then this one is even bigger, then this one is the biggest. Any questions with 4b? All right, we have a couple of applications now. Usually in Math 30-1, what you are given in terms of logarithmic applications in terms of an expectation is you are given a formula containing a logarithm and asked to apply it. So I don't know if anybody has welded before. A lot of the newer technology with welding helmets have an electronic welding shade that only allows a certain amount of light through based on polarization of light. However, there are actual pieces of glass which are called welder's glass. And a number 14 welder's glass is what you would look through if you wanted to look at the sun. If you look at the sun, and for goodness sake, don't look at the sun. But if a person were dumb enough to look at the sun with their naked eyes, which means they're not wearing any kind of eye protection, you will permanently damage your eyes. You can go permanently blind. You'll have these bright spots where the sun is, and they will be burned onto the retina of your eyeballs. So don't do that. But you can look through a number 14 welder's glass. When you do look through a number 14 welder's glass, if you had a welding helmet on and the number 14 welder's glass and you tried to walk around in your day-to-day life, you'd be bumping into everything. You can't see anything. It allows very little light through. So in this formula, S is the shade number. In this particular question, the shade number is 14, and what we are asked to find out is what T is. And T represents the proportion of light that goes through the welding glass. So as I'm saying in the example, if T is 0.333, it only allows 1/3 of the light through. Bottom line is we're going to use this formula. We're going to put 14 in for S. I'm going to move this negative here out in front and put it with the 7. So -7 times log of T over 3 plus 1. And I'm going to just show something to you here. I hope it makes sense. If I gave you the following equation, I said, find X. That really shouldn't be a problem. The first thing you would do is you would subtract 1 from both sides, and you would end up with 13 equals -7x over 3. And then you would multiply both sides by 3 and divide both sides by 7. Can you guys do that for me, please? Take 13 times 3 and divide by the -7. I think I said divide by 7. I meant divide by -7. By my count, you're going to get something like -4 point. I don't know. Is it -5.1428? Does anybody else agree in that? I just want to make sure before we move on. -5. So we're getting a couple of different answers here. -5.6, -5.6, -5.57. Okay. So bottom line here is, and I don't, oh, there it is. But I don't need to worry about what the actual decimal is. It's going to be 3 times 13, which is 39. I'll have 39 over -7. It's this number. Would be equal to X, right? But now we got to give our heads a shake and come back to reality. And you would think it shouldn't matter, but unless I explain that to people, people get stuck. They don't know what to do. What you are doing is you're rearranging for log of T. So you're subtracting 1 from both sides to get 13 equals -7 log of T over 3. Just want to make sure that's the right formula, and it is. Then you're taking 13 times 3, which gives you 39, pretty sure, divided by -7, gives you -39/7, which is log of T. And then people go, I don't know what to do. I don't know how to get T. You have to remember this is a base 10 logarithm. And if you don't know what to do now, then you rewrite everything in exponential form. 10 raised to this number is equal to the proportion of light that gets through this welding glass. And now we can figure out the answer. You're going to need to, of course, put -39 over 7 in brackets. You get a very small number. It's times 10 to the -6, which means it's 0.000027 is the proportion of light that gets through this welding glass. If I convert that to a percent by multiplying by 100, I mean, it's not even 1%. It's like, I want to say it's 2 to 3 1,000ths of 1%. So it's a very small amount of light. But does anybody have any questions with how we solved that equation? There's all of our work. All right, the final question in this first lesson today says there's a logarithmic relationship between butterflies and flowers. And the first time I saw this, I kind of laughed and said, you gotta be kidding. I've seen some very contrived math examples that teachers make up, but this takes the cake. But it's true. I thought this was made up. This is the graph of the data from the study that was done. And on the horizontal axis, on a number of different days, the biologists counted how many butterflies there were in a particular garden, and they averaged them. And they counted how many different species of flowers were present in that garden. And then they moved to a different garden in a different location. This was done in Great Britain. They moved to a different garden, and they collected the data in that garden, and they moved to a different garden and they collected it. And you get a logarithmic relationship. And the logarithmic relationship is given by this formula. It says that the number of species of flowers is equal to negative 2.641 plus 8.958 multiplied by the base 10 logarithm of the number of butterflies they counted. So the question is, if f is 25, what is b? That's what the question is. So you're going to put 25 here. And what I would like everybody to do, just to begin with, I don't want to do all the work here for you, is I want you to rearrange this so that you have a statement that says log base b, log base 10 of b rather, is equal to a single number. And if you have difficulty in deciding how you're going to do that, then just pretend that this is x and find x. So I'm going to give everybody 10 seconds or so to rearrange that for log base 10 of b. And when you do get the number, you can feel free to type it into the Google chat. Yeah, I'm thinking it's around 3 point something as well. When I add the 2 to both sides, I get pretty close to 27. We have to divide 27 by pretty close to 9. I haven't confirmed that yet, and I'm still waiting for some other people to type in what they get. What you're going to have to do is take 25 and add 2.641. Get 3.085. Okay. Like I've said before, math is not a democracy, but I'm usually, when almost everybody gets the same answer, that's correct. No problem, Aiden. So, as I amply demonstrate almost on a daily basis, it's very easy to make mistakes. We're going to take 25 and add the 2.641. I hope I wrote those numbers down right. I better look up here just to make sure. And you have to hit equals in between unless you're willing to commit to brackets. Then I have to divide that by 8.958. And I get, 3.0856 roundabout. Now I put the base 10 in here. I'll put a dot over the equal sign because it's not exactly equal. I put a base 10 in there, but very often, well, it's never written there. There's never any base. So people get to this point and they go, I don't know what to do. Well, let me show you a different approach. If you had, forget about quadrants, coordinate trigonometry, identities, all that reference angle stuff, forget about that. You're in grade 9 and your teacher says sine of some angle equals 0.5. What do you do on your calculator? You go second sine to get the angle. So what do you do here to get b? You go second log of 3.08 whatever. But look at your calculator. When you go second log, what happens? 10 raised to the pops up, which I hope makes sense because this is log base 10. So when you write this, got a lot going on here, so I'll do a little bit of highlighting. When you write this in exponential form, you're going to write 10 raised to that number equals b. And that's what happens when you go inverse log of that number. So if there were 25 different flower species, you would expect there to be around 1,200. It's not exact, right? You're not going to have 1,217.928 of a butterfly, like some kind of part of a butterfly sitting there on the ground. You'd probably just round it to 1,218. Any questions with that last example? All right, so that's the first lesson today. Again, it covers quite a few ideas. Transforming logarithmic functions, using the change of base formula, and also applications. One more thing, it just occurred to me. I said I would try to remember something, and I'm going to. If you go back and look at this graph right here, could you use your graphing calculator to graph this? Absolutely. Because log base 2 of 2x plus 6 is log base 10 of 2x plus 6 over log base 10 of 2. I don't want to spend our time together doing this, but if you put that in for y1, you do not get something that looks good. You do not get that. You get this. And what this, it's really deceptive. What this deceives you into believing is that when you graph that on your calculator, it starts right here. And it doesn't. There's an asymptote here. Your calculator just can't cope with it. A little bit later on today, I will show you something else that you can do on your calculator. But for the next 10, 15 minutes, I'll say 10 to 15, and I'll let you know in a few minutes how it's going. These are the questions you're working on in this lesson.